Yeah, okay. Yeah, am I audible? Suspense or not?
Yeah, we are on
Okay,
that.
okay. Yeah, good evening, everyone. Welcome to the week 6 programming assignment solution. So today we will discuss the graded programming assignment of week 6. And we will also explain the week 7 programming assignment problem statement. Yeah, okay. So Sadat, you can start.
Yeah. Just a minute. Yes. Open visible, right?
Sanat, your
Yes.
voice is breaking, I think. Pushpin,
Is it fine now? Is it fine?
Yeah, even I hear the break sound.
yes, not clear.
Is it fine now? Or like again? So
No, no,
let me
no.
then rejoin.
We can't make out anything.
Now is it
Sana.
fine, right? Okay.
Yes,
Okay, wait. Let me rejoin.
yes, yes.
Yeah. Just
Yeah, Pushpin, can you start? Well, Sanat will join.
Sure, give me a second. Share my screen. Let me know when it's visible.
Yes, yes. Yeah, it's visible.
Okay. So the week 6 problem was a simple one. The statement goes something like Mr. Seven has a large farm which is divided into small areas, and each area is watered through channels. Help Mr. Seven to find out the minimum time it would require to take for water to reach each area in the farm from the given source of water. If it need, it is possible. Now each area is denoted by a node labeled from 0 to n minus 1, and each directed edge represents the direction in which the water will flow from the source area via channel into that destination area. The weight of each edge represents the time it would take to reach from the source area to the destination area in probably minutes, not seconds. So this is the representation graph that was used in the problem statement. So you have 4 nodes labeled 0, 1, 2, 3, and you had a directed edge from 1 to 0, a directed edge from 1 to 2, and similarly from 2 to 3. In this example statement, each of the edge weights were equal to 1. So the problem statement is in which, in this case, you would be given a source from where you would be starting, and you need to figure out what would be the time by which each of these nodes would be uh, traversed, meaning they would reach, water would reach to all these farms in the example statement. So if I'm given the source 1, when I'm entering the when I've specified the source 1, I would add the edges from 1 to 2 and 1 to 0 into the priority queue. The priority queue would then return me the minimum the edge weight which has the minimum distance. In this case, both of them have the same distance, so it won't matter in this case which edge is returned to us. So in this, let's assume that we got an edge from 1 to 0. We add the 1 to the from 1 to 0, the time it would take from water to flow from one first node to the 0th node. Then we remove that from the priority queue, and then we add any outgoing edges from 0. Now 0 doesn't have any outgoing edges from 0. So in that case, the minimum distance would be from 1 to 0 is 1 only. Now the priority queue would then give us the next edge, which would be 1 to 2. And in this case, we would add the edge from 2 to 3 because there is an outgoing edge. And by that same logic, we'll the minimum time it would take from 1 to 2 is 1 at this point of time. We'll get the next node, which is meaning there's only one node remaining in the priority queue, so we get the edge from 2 to 3, which is again 1, and that is the end of the entire traversal. So, and because there is no outgoing edges from 3, that is the complete, and what we get the minimum time, it would be the 1 plus the maximum edge that we have here, which is this particular path. 1 plus 1 is equal to 2. So 2 would be the minimum time it would take for all all the farms to be watered. Now, if there was a condition that because these are directed edges, it might be possible that the source, not all the farms would be possibly watered if it is chosen as a source. Now, if we choose source other than 1, like probably 2, and or probably even 0 or 3, there would be a subset of those farms that would be watered. So if we take this 2 as an example, there's only one outgoing edge from 2 to 3, and these are the only 2 farms, so the output would be -1. So this is the dry run of the example. I'm hoping there isn't any questions in the chat or anywhere. So let's have a dry run of the code as well. So what we have, this is just the adjacency list, a representation of the entire graph, where we get the let me also go to the input format. So you have this format where you're given the number of nodes and the source vertex as the first line of input. The next n lines has a representation of the edges connected to that ith node. So as you can see, the first 0th node in this case has no outgoing edges, as represented here as well. The first node, in the first node has two edges, which is from 1 to 0 and 1 to 2. So this is the destination, and this is the edge weight between that source and destination. So you have two edges going outwards from 1, which are these, to 0 and 2, and each has 1 as the weight edge weight. The second node has only one outgoing edge, which is represented by 1 here, and it goes from 2 to 3 and has an edge weight of 1. The third node has 0 outgoing edges. And so this is the input format that we have. So what we are doing here is just we're taking the input, we get the number of vertices, we get the source from which we're using as the source farm, and now we get the each line, take the total number of neighbors, which is the first input. Then we take the destination and the weight as a second and third for each of those total number of neighbors. The next is just populating distance with some insanely high number so that we can build our priority queue. We set the destination for distance for the source itself as 0 because it's the source itself. We initialize a priority queue. We add the distance we actually put all the vertices at first within the priority queue with the distance. So only the source would have 0, rest everyone would have an infinite value. Now we get the minimum from this priority queue. We check whether this is a sort of a sanity check condition, because we are always pushing values instead of actually deleting it. If you notice from the any existing value. So let's assume there is a node vertex 1 which had an infinite. So we're not replacing it. We are just making sure that if the distance of that to that vertex is already less than the distance that we get from that priority queue, then we just ignore that value. Now for each edge, we figure out what are the adjacent edges for that vertex. We check whether the distance that we are adding to that, we add the distance of V and the edge weight to that particular edge. And if that distance is maximum than the current edge, then we don't do anything. I hope I'm making sense. So if that's not the case, that means that the distance itself from, if we have, let's assume that, let's modify the terms given another edge. Let's imagine So what would happen in this case is that when we're coming in at this point of time, we check whether the edge itself uh, is less than the current weight itself. So if we look at this particular problem statement, we have chosen source as 1. Now from 1 to 2, the maximum distance is currently 3. But if we go from 1 to 1, 0, and we choose the path from 1, 0, 2, the minimum would be 2. So this is what exactly it is doing. If it is actually greater than, it would ignore, meaning if the value itself is, let's assume this was 5, then it would ignore this update to this distance from 1 for 2. If not, it would actually update it. This is what this particular line is doing, which means that the current distance, if we add the current weight to this distance, then we still have the minimum, which is then subsequently put into your priority queue, and you go to that priority queue until it is empty, and the rest is just figuring out what is the minimum value across each of the distances that we have populated in the distance array. I hope this this made sense. Okay, so let's check the chat. I hope there isn't any questions from anyone. Thanks. So what I'll do is now go over with the not the practice, but the assignment for week 7. Okay, so the problem statement goes something like this, Mr. It's almost based on the week 6 on similar lines. They have the same setup in terms of the problem statement. Mr. 7, so I'll go through it once. Mr. 7 has a big farm which is divided into n small areas labeled from 1 to n. Mr. 7 this time is planning to construct channels instead of letting nature take its course. So these channels would be used to feed water into n areas. Now construction does not come free. Help Mr. 7 figure out the minimum cost he would have to bear for this construction, given that the channel's width would be 2 meters. Mr. 7's requirement can be modeled into a graph where each area is denoted by a node and each edge represents a possible option for channel between 2 areas. The weight of each edge represents the length of the channel in meters. In the below figure, there are 2 possible paths for water to flow within the channel. That is either directly from 2 to 4, which is this, or via the path 2, 3, 4. So the output needs to produce the minimum cost involved in the construction, given all the available choices for Mr. 7 to choose from. So this is the representation graph which we have used in the problem statement, and the idea here is that, first of all, these are undirected edges, and these are like possible routes where which would be utilized during the construction. So this is sort of a plan. So there won't be 2 edges leading to the same vertex. So this and this is not going to fly, because what we're looking is the minimum cost here. So if we were to go from 2 to 1, that would make sense. From 2 to 3, we have 2 choices, either from this or this. Obviously 5 is less, so we would be choosing. I think I've explained in this problem statement as well. But before that explanation, I'll go to the input format. So what we are given here is like the format goes something like, we have the total number of nodes, number of edges, and the cost of construction per meter square. So, and each next 4 lines, which is representing the edge, would be like source destination and the weight of that edge. So there's an edge between 1 to 2, which is 3, 2 to 3, that is 5, 3 to 4, that is 9, which comes around like somewhat similar to what we have used in the graph. Now, if you look at this in this, we have these edges 1 to 2, 2 to 5, 3 to 4, and 2 to 4 as well. But what we are looking for is the minimum. So we would have to choose the minimum, which gives us the minimum cost of construction. So we would be taking 2 to 1, 2 to 3, and 3 to 4. We won't be taking 3. What is this? Right. This particular 2 to 4, because it would increase the cost as well. So if you look at this, if you were to do this 3, 5, 8, and at this edge, it would give you 19. However, if you were to take this 1, second to 1, second to third, and third to 4, you would get a sum of 17 meters. Now, what we the problem statement has is the channel needs to be 2 meters wide. So you just have to multiply the total length that you have figured, which is the minimum construction it would take, and multiply with that 2, which would give you the total area to be constructed. Now, what you need to output is the cost of that construction, which would essentially be multiplying the cost per meter square with the area that the channel needs to be constructed with, which would turn out to be 1020. Any questions on the problem statement? Any would do, if it makes sense. Okay. No more questions. Stop sharing my screen. Sanath, you can take over. Yes.
Yeah, Sanath, can you go? Can you start?
Yeah, sure. Yeah, sure. Is it visible? Is my voice okay now? Hello?
Sanath, still your voice is not clear.
What is this Zoom actually? It takes a lot of, I don't know why this. Stop sharing. Is it fine or is it okay?
No, it's not fine.
Anand, right now you sound like a robot from a future. I think probably the audio is off or something.
Now is it fine or
There's an unpredictable
Now-
break in video voice.
what about now? Like, is it?
No, Sanath. Sanath, one thing you can do. You can join through the phone also and share the screen from laptop and.
Yeah, the point is I don't have Zoom on my phone, so I don't know where is that. Let me check this. Yeah, 1 minute. Just 2 minutes, like again. I mean, still it's breaking, right?
Yes.
Probably you can try restarting your machine. It might work.
Yeah, I did that, but still I don't know what is that counting. I don't. It just says it's consuming a lot of CPU. Just a minute. I'll join through phone maybe and I'll share my screen here. But not so much.
So now you can hear me, right?
Yes, Anna.
Yeah, much better.
Yeah, wait a minute. Yeah, now I can hear. I don't know. I just mute this audio. Um, Yes, I'm like, you can hear me right now. You can hear me right now.
Yes, yes.
Yeah, now it's fine. Yeah, there's no echo also, right?
No. Yeah. Fine now.
Yeah. Let me share my screen then. What's the problem with this Zoom? So, I think so Matt have to quit again and join it. This got stuck. Let me do. Can you make me again the co-host?
Yes.
Yeah.
Yeah, you
No,
can say.
yeah, this, yeah, now. That. Now it's visible, right?
Yes.
Yeah. So let's actually discuss the problem then. So the problem states that we are imagine we are training a robot with the help of reinforcement learning to understand a plan of the Chennai city. Most of the RL model needs something called feedback. So to give this feedback, we have to get an algorithmic solution. So what we have to do is we have something like a Chennai city and we have some list of nodes and assume that IIT Madras is always the node one. And what we have to do is we can wander from one place to another through these bidirectional edges. And whenever we say visit a new place or say new area, we have to record it. And what our say recorded permutation should be is lexicographically smallest sequence. For example, let me have this test case. Maybe we have 1, 2, say 3, 4, everything. We can start from 1 and we can go, suppose say 1 to 7, then 7 to 2, then 2 to 7 basically, because we cannot go anywhere from 2, and then we'll go to 4, then 3. As we from here we can go to 10 too, but we can say that 4 to 3 is lexicographically smaller sequence than 4 to 10. So that's how we can think of this thing. Let me maybe give a white board. So so we have nodes literally. Suppose say 1, 2, right, properly. 1, 2, 3, then I have 4, then maybe see 5. I have like this. So what I can do is here actually I can move from 1 to 2 to 3, then I can move to say 4, then I can move to 5. So we have to get this order. This may not be always, say, for example, here we can say like 1 to 7, 7 to 2, then we are going from 7 to 4. Then instead of 10, as we find 3 is lexicographically smaller, we go there. So then 3 to, now we can go to 9. But the point is we can actually have a better lexicographical order by adding 5 instead of, say 9. So we'll go from 3 to 4, 4 to 5, then 5 to 4, 4 to 3, 3 to 9, then we can go to 10. So these will not be actually added because only the starting from 1 where and all we can reach, only that component should be, we have to print it, the other components we need not print it. So let's actually dive into the code maybe first. So here is a Python code. So what I'm doing here is, so I have something called, say a function solve, which inputs, of course, the n and m, where n is the number of nodes and m is the number of edges, and I'm creating a say matrix for say adjacency list, if I'm not wrong. So now then for I in range of m, that is the number of edges, what I basically do is I input the say vertices here, and then I have I append it to the adjacency list, and then I have my visitor basically. So now what I can do is I can think of the lexicographical order as my weight. Instead of normal weight, I have something called like this order, the lexicographical order which we used to say get. This I can actually think of a weight and try to arrange my say my solution based on this. So if suppose that is the thing, we in any data structure we can any language we can implement something called heap, or especially a min heap, to store our values, and then I call it as your priority queue, and I push the value 1 into the priority queue. Now what this priority queue is about is it's a min heap, where I'll always have a minimum value in the priority queue as the first element. So when I pop the element from the priority queue, I'll always get the most minimum element which is stored in the queue. So then I'll append it to the result j, and then I'll again visit it and then push this. This keeps on happening all over the iterations, and I get finally my lexicographically smallest order of every case. This is what it happens. So when I wanted to explain a lot, this actually has the queue. This is the whole queue basically, and I treat it as a heap, and this queue only has the smallest value. And basically I believe there is nothing much complicated in this solution. If suppose people can't understand, I think they can just raise me, or they can give me any chat. I can see the chat box too. There are no chats. So suppose with, I think so this is a very easy question. It's not, you can find the weights properly, then I believe this is. And let me explain the week 7 question too. So yes. So let's discuss what week 7 says. Imagine you are working in Meta and your boss wants the results of how strong a component of friends in a social network can be in terms of the amount of messages sent by each. So you have maybe say you're working in a company, and which is like a Facebook company, and you wanted to find the strongest component. So boss gives a weird metric where though the connected component can as many edges, he wanted you to limit it down to exactly n-1 edges, where n is the number of vertices of the connected component. So he just wants the component which actually connect. He need exactly n-1 edges which can connect the whole component, and remaining edges can be eradicated. While limiting down to the n-1 edges, the total cost of each component should be made minimum. So in some sense, this says that we have to find a minimum spanning tree, and with various components. We have to find the minimum spanning tree among the component, and there will be so many components in the graph, and we have to find the minimum spanning tree in all the components, and we have to get the most say maximum cost of the say minimum spanning tree among all the components. I believe we could see the example we could get it. So suppose we have this is our graph, and this is our first minimum component which actually has 19 as the total cost, and this is our second minimum component which actually has 4 as a total cost, and the 0 the third minimum component which has 0. So our answer should be 19. So this is what the agenda of this question, and I believe this is understandable. Is it fine? Suppose it's fine, then I'll stop sharing my screen.
Yeah, okay. So any question from those who have joined? Okay. So fine. So now no more questions. So we can wind up the session. So if you have any doubt in any problems, this assignment problems or theory assignment problems, you can also post on the forum, either on Google and Discord forums. So you can post, we will reply on that. Okay, so we will meet in the next week for the week 7 session. Okay, thanks Pushpin, thanks Sarna.
Thank you.
Bye.
Yeah, bye.
Sorry for the technical
Sorry.
difficulties.
No, it's happening.